Swayam Prabha. Digital India. Educated India.
Work conversion devices. This is the, you can take any one example, take the Otto cycle, so called Otto cycle. This is the one on which your gasoline cars still operate. So I have P versus V. What I have is a piston cylinder assembly. The piston moves up and down. The normal procedure is for you to have two valves. You can have now 16 valves or even 32 valves. Anyway, one is called an inlet valve, this is the outlet valve. These are the details that Carnot refused to get into. They told him, what's your engine? He said, I don't care. Really frustrated people back in. You are talking of thought experiments and abstract thinking in universities, now you take it for granted. I mean, every other joker tells you do a thought experiment. But you must realize that when Carnot did it first, nobody ever thought that you could discuss a heat engine meaningfully without an actual engine. But anyway, this is just for concreteness. There is a piston cylinder assembly, this moves up and down. The strokes are like this. First you have, at atmospheric pressure, you have an intake stroke. Let us draw some figures. This is clearance volume, that is the, when this cylinder reaches the top dead center, this place is called top dead center, TDC. The cylinder is shaped in such a manner that you have actually a small dead volume there, it is called clearance volume. And for example, one of the achievements of Japanese manufacturers is to reduce the clearance volume and show you the efficiency increases tremendously. So there is a clearance volume, this is a design specification, you can make it as small as you are capable of. It can't be made 0, but subject to that. Then from here you open the inlet valve, keep the outlet valve closed, then the gas is taken in, the air is taken in typically, and the cylinder moves outward. So the volume increases, it moves to some point here. So this is the inlet stroke. Stroke is simply movement of the piston, a stroke during which the air is taken in and then the valve is closed. Here the inlet valve is open, the outlet valve is closed. At this point you close both the valves, then you have an adiabatic compression. At this point in a gasoline engine, you have a spark plug. A spark is created across the spark plug. I do not know how many of you have seen a spark plug. The spacing is, we used to do it in inches, it is about 1/10 of a millimeter spacing, or actually it can be up to a millimeter, but it is less, much less usually. A spark is actually, you have a induction coil that generates very high voltage and a spark crosses this, and that spark ignites the fuel. At this stage this air is actually a fuel air mixture. Nowadays what you have is an injection device that injects the fuel as well, because it measures the fuel exactly. Normally in the classical engines, and we still have a few of them, the air that comes in, through a carburetor. The word may go out of the dictionary soon. so you may not even need to know it. The carburetor, what it does is measures the, if you put your pedal to the metal, then a lot of fuel will be taken in. If you relax on the accelerator, only a few drops of fuel will be taken in. That is actually controlled by a beautiful mechanism. If you have seen any of the, I think I am talking to you in a language of before you were born practically. This actually till last 10 years ago there were carbureted engines, even now you have carbureted engines. The carburetor usually has a needle valve, it is a very nice mechanism. You have a valve that looks like this, there is a tank that contains the liquid, and as this valve goes up and down, the air flows over the thing. As this goes up and down, you have exposure of the liquid. The exposure of the liquid will vary, I should make this narrower, then the amount of fuel picked up by the air will depend on the surface area of the fuel. So it will vary. I am drawing an absurd picture, you have to actually see the carburetor properly, I will get a picture for you. Anyway, that is controlled. So at this stage, this is a fuel air mixture, very small amount of fuel and air, enough air to combust the fuel, and normally you have excess air because you want the pressure, the fuel is too precious, so you want complete combustion. So if you suddenly press the accelerator, you often do not have enough air, so you get a smell in the exhaust. But anyway, at this stage the sparking is done. When sparking is done, in the auto engine, the ignition is, this is ignition stage. So this is adiabatic compression, then this is ignition. The ignition is so rapid that the cylinder that comes up to the top does not move back during the time of ignition. Okay, the time of ignition is really small, so effectively it is constant volume ignition, that is the characteristic of the Otto cycle. As far as thermodynamics is concerned, this is where the reaction occurs. The reaction products have much lower internal energy than the product coming in, so the difference appears as heat. Because no work is done, delta Q is equal to du in this process. So the change in internal energy is what is supplied as heat. Normally you call it constant volume heat addition. In the case of a diesel engine, this actually, this pressure is much higher and the ignition is supposed to be at constant pressure, because as you inject the diesel it burns by spontaneous combustion and that takes longer than spark ignition. So actually the piston moves back and the pressure is maintained. Incidentally, this is what they will do when they tune a carburetor. They can tune a carburetor for you to get better acceleration. I mean, they can tune the engine. What they do is to say that this fuel intake, I am sorry, this ignition, the spark ignition, the spark will be ignited a little before the piston reaches the top dead center, so that the ignition occurs exactly when the pressure is maximum. It is measured in degrees because you have a dial on top which is turned. They will say 5 degrees. If you talk to these mechanics, they are pretty clever guys, they do not know exactly what is going on inside, but he will tell you how much advance to keep and so on. It is particularly effective in your motorcycles, keeps a little more advance and it will go bang, much better. There is a big difference. If you make it too, if the ignition is too far in advance, then before the piston reaches the top dead center it will be sent back, so you lose some power in that process. Okay, anyway, you get to this, you get ignition, then you have adiabatic expansion. This is adiabatic, meaning it occurs in such a short time that there is no time for exchange of heat to the surroundings. And then this is simply cooling. This is your radiator fluid. If you have an old Volkswagen Beetle, it does air cooling very effectively, simply with more fins. And then there is a exhaust stroke, the inlet stroke and the exhaust stroke. The exhaust stroke pushes out all the material inside this piston, and actually nitrogen is the same, part of the oxygen will be consumed, replaced by carbon dioxide. And since your fuel also has a bit of hydrogen, you will have some water in the exhaust. but if you ignore the inlet and the outlet strokes and simply look at this cycle, it is a closed cycle. If you pretend instead of change in composition does not really change the specific heats significantly. So it is air plus whatever, or just call it air, with a certain specific heat that goes through a cycle, and here you have heat addition, that is, instead of the reaction that produces a change in internal energy that gives you the heat, you just call it heat addition, and this heat addition, and here it is heat removal. So effectively you have an adiabatic compression followed by heat addition at constant volume, and then you have an expansion. So this expansion will give you work. On this diagram you will calculate work as PdV. So the area under this curve is the work done by the system, the area under this curve is the work done on the system, because you have to compress it, which is why we always have an electric motor to get the whole thing started. You crank the motor, it compresses it first. Once this heat addition occurs, then there is enough energy, then it goes out here and then it can keep going. So the net work done is this, the area under that curve is the net work done in the cycle. So this volume here, we will call these various points by name, call this A, we will start here, A, B, C and D. A, B, C, D is your cycle. This volume is called the stroke volume, simply measured by the pi d squared by 4 into the length of the, it is the volume swept by the piston in a movement. The quantity of interest is how much heat do you add here. We write this in terms of Q. In actual fact it is a reaction occurring where, as I told you, the internal energy of the products is less than the internal energy of the reactants, and therefore you get net heat added to the system, but we calculate it in terms of heat added and work done. The heat added divided by the calorific value of the fuel will give you the amount of fuel consumed. So effectively per fuel consumption, what is the amount of work you can do, what is the mileage you get and so on. So this is the one that I want to analyze. This is the original cycle proposed by Otto. So what you do is, in order to do the analysis, I will write AB, all the equations are given on, this is a closed system, delta Q minus delta W, that is it as far as I am concerned. So the stroke AB, I am going to ignore the inlet and the outlet strokes as cancelling one another, I do not have to consider them at all. I pretend that here I start at A, I pretend instead of fuel ignition I pretend heat addition, and I pretend here that there is heat removal, which is actually the truth, I remove it very quickly. AB is an adiabatic system, so delta Q is 0, so delta W is equal to du. If I assume ideal gas, I do not have to, there is actually thermodynamic charts for this which you can use, but if you assume ideal gas you are talking of Cv dt. Then I have Bc, or I will write W itself, WAB. So I can integrate this, WAB is simply Cv into T2 TB minus TA. See, if Cv is constant, you use an average value of Cv, otherwise you have to, it's strictly a function of temperature, but for all practical purposes in engineering we use average values of Cv to do the integration. Then I have Bc, sorry here, Bc is simply constant volume heat addition, It is actually not heat addition, as I told you, it is simply a reaction occurring. Your carbon will go to carbon dioxide, the hydrogen in the fuel will go to water, and the change in internal energy is equal to the heat added. So again, if you like, delta Q is actually equal to du, or heat addition is simply integral of again Cv into Tc minus Tb. The conditions at A are known, the pressure at the intake is known, it is usually atmospheric. And this can be, when you have a supercharged engine, all you do is have a compressor and raise this level, and I can show you that gives you more power per cycle, but at the cost of more fuel. It does not make it more efficient, but you get, so initial that kick you can get by supercharging your engine, putting a compressor in the outlet, compressing the inlet gas and sending it in, inlet air and sending it in. Then CD is again an adiabatic process. You have WCD, there is a minus sign here because du is minus delta W. So this is minus, okay. Then WCD is exactly like here, I can simply write it down, this is Cv into Td minus Tc. Because Td is less than Tc, this will turn out to be positive, that will turn out to be negative. And last one is dA, this is again Q, this is QBC, this is QdA. dA is exactly like this, Cv into Ta minus Td. So what I am looking at is, I am interested in is W net by QBC, because QdA is simply heat lost to the environment, I get nothing from it, but QBC is what I supply, that is my fuel. So remember, QBC by calorific value of fuel will give me mass of fuel. So if I want work done per unit fuel consumption, I will essentially have to calculate W net. W net is essentially WCD minus WAB by QBC. So you get Tc minus Td minus, I have WAB minus Tb minus Ta. I have taken the minus sign out by switching, divided by QBC is Tc minus Tb. So this is 1 minus Td minus Ta by Tc minus Tb. So this is your efficiency. All you need to do is calculate the temperatures, and you can calculate these temperatures very easily because Ta is known, Ta and Pa are known. This is adiabatic, so you have your formula PV per gamma is constant. So from here to here you know this volume, so you can calculate the final pressure here. So once you calculate the pressure, your T is again PV is equal to RT. Then here again this temperature is known, this temperature is not directly known unless you know the heat addition, that depends on how much fuel you add. So I can give you the fuel consumed, you can multiply it by its calorific value and put in Q here, and so you can get this temperature actually backwards from this equation. That is, I know TB, now I can calculate TC is equal to TB plus QBC by CV. So I can calculate that temperature. So I can calculate these conditions and then these conditions again, this is an adiabatic expansion. Once I know these two I can calculate here, because everywhere the volume is fixed, it is fixed by the geometry of the system. So when they say 1.3 liter engine, they usually mean this is 1.3 liters Vs. So if you have a BMW 6 5.3.0, 5 is the series, then 3.0 liters, 3 liter engine, it's supposed to be a very big engine. And the compression ratio also determines the pressure from here to here. Depending on this ratio you get higher or lower pressures. And if you look at this clearance volume, it has physically a bad influence, because at the end of the process when you compress it, you have clearance, you have gases at the end of this process at this pressure and at this volume. So when you expand it out, this gas remains, when you finally expand it out, that gas remains in the system, and so it occupies space much more. At atmospheric pressure it occupies more space than it would before. So essentially it represents a loss, because you have the spent fuel air mixture that is still occupying the space inside the cylinder. So clearance volume represents loss. What we can do is work this out in terms of geometric specifications. As far as possible you get all the variables in terms of geometric specifications. We will do that. So we will just calculate each of these temperatures, then I can get these ratios. TA, I am wondering, okay, TA is known. I should have done it in terms of, it is okay. I will leave TA as it is. TB, what is the formula? It is PV per gamma is equal to constant, and PV is equal to RT. N is constant here, the number of moles is constant. So I want V-T relationship, that is all. So instead of P I write by V per gamma minus 1. So T V per gamma minus 1 is equal to constant, right. So TB, if I am writing in terms of TA, TB is simply TA into VA by VB to the power gamma minus 1. VA, VB are geometric specifications. If I give you the cylinder dimensions, then I have given you all the data for VA and VB. Then similarly, I suppose I should have kept TC comes out in terms of heat addition. Okay, I will try and use this equation rather than this. So I have got TB in terms of TA. Similarly, TD is equal to TC into the same ratio. VC, VD are the same ratio as VA and VB. So TC, VC is VB, VB by VA to the power gamma minus 1. You want VA by VB, so I will write everything in terms of Tc here, or this is Td, that is efficiency is equal to, if I pull out a Td, this will become Tc by Td, which is Va by Vb. We will call Va by Vb as R. It is a geometric specification. So I have Td into Tc is R to the power gamma minus 1 minus Ta into Tb by Ta is Va by, I want Vb by Va, so minus Tb. I will pull out this Tb into 1 minus Ta is a smaller one, it is Vb by Va. No, Va by Vb is R, so this is correct. What I wrote is right first. Ta into R to the power gamma minus 1 divided by Tc minus Tb
by taking Va and Vb to the other side.
Are you manipulating this equation or this one?
The lower one.
This one.
Yeah.
Okay. What do you want?
So
You want?
So D in terms of Tb, sir.
Okay, Ta in terms of Tb, that is already written right here.
But you take this Va and Vb to the other side, and then you write
TA is
You want Ta,
so left
I have written that Ta is Tb
R
into R to the power gamma minus 1, I have written that.
1 minus gamma.
Pardon?
Actually it will be Vb by Va, so that's R raised to minus 1.
Ta is Tb into Vb by Va, so 1 by R to the power gamma minus 1, right? Okay. That this equation I have written Ta, then
And said similarly Td is also Td is equal to Tc by R raised to gamma minus 1. So you have R raised to gamma minus 1 coming out, and then numerator.
R right, okay. 1 by R to the power gamma minus 1 comes out. You are now doing this equation?
Yes, sir.
Okay, Td minus Ta, yeah, so you got, yeah, thanks. So eta is equal to 1 minus Td and Ta is Tb minus Tc minus Tb into 1 by R raised to the power gamma minus 1 divided by Tc minus Tb. Yeah, thanks. So you have efficiency equal to 1 minus 1 by R to the power gamma minus 1. R is what you have control over, because you are building this. So your R is actually Vs plus Vc, this is stroke volume, this is clearance volume. If you want, I will call this VCL to make it clear, because we have another Vc by V clearance. Clearance volume is the dead volume, if you like, when the piston is at the top. So this ratio is in your control. Actual practice, what happens is that these things are rounded off. It does not happen exactly like this, because the actual stroke, the valve has to close, it takes some finite time and so on. But if you look at the whole process, it is sort of controlled. If you are talking of 3000 rpm, you got one explosion about for every rotation of the crankshaft of the wheel, not the wheel, the crankshaft, because then the wheel is geared, but for every rotation of the crankshaft you have 2 explosions, and you are talking of, if you 1000 rpm, you are talking of 2000 controlled explosions per minute. So that is how your vehicle runs through a series of controlled explosions. every time you have the fuel burning you have a small explosion, it is all contained. The other cycle that one can discuss, incidentally the Carnot efficiency, the efficiency here is 1 minus 1 by r to the power gamma minus 1. Of course the other way of changing this is to use a fluid that has a different gamma, but other than air anything else you use you are going to pay heavily, so there is no point in trying. Unfortunately air and oxygen have the same gamma, otherwise you can try purifying and using oxygen, but in any case it does not make sense. So this is the only thing. The Carnot efficiency is you have to take the highest temperature as the source and the lowest temperature as the sink, equivalent Carnot efficiency. So will be 1 minus the lowest would be Ta by Tc. So do you have an expression for Ta by Tc? 1 minus Ta by Tc would be written in terms of Ta by Tb into Tb by Tc. I do not like Tb by Tc, I suppose I do not have a choice. This is 1 minus Ta by Tb is 1 by r to the power gamma minus 1 again into Tb by Tc. So Tb by Tc is less than 1 and therefore your Carnot efficiency is greater than the efficiency that you get from the Otto cycle analysis directly. The diesel cycle is actually similar, except that you have two parameters for control. You have a Vs and a Vc, again it is the same construction. You have the exhaust stroke and the inlet stroke. What you have is a compression, adiabatic compression. At this stage the fuel is now added by injection and you cut off the fuel injection at some point and then it goes like this. So here it is constant pressure heat addition. The word heat addition is used to denote the change in internal energy that occurs during combustion. So you have the same A, B, C, D. Usually these pressures are much higher, so the diesel engine has to, the block has to be much heavier in order to withstand that pressure. And there is a cutoff ratio here. This ratio of the volume here C, this is clearance, Vc by Vs plus Vcl is defined as a cutoff ratio Rc. It is the time at which you cut off your diesel, that depends on how much you press your pedal. And you can show, there is just a lot of algebra, you can show that it is always less than this. For Rc, when the Rc is equal to this, when this is equal to 1 by, what did we call this, V clearance by Vs, is that what we called R? Yeah, so when it is equal to R you will find that the efficiency is same as an Otto engine. So in general the efficiency of a diesel engine is less than the efficiency of an Otto engine for the same R. On a, actually there is an air standard cycle table from which you take thermodynamic properties, so you can actually calculate the, you can take the non-idealities into account, because you are doing this ideal gas analysis here. At this point it can be an ideal gas, but at the higher pressures it will not be an ideal gas, there is some departures from ideal gas, but these have been computed and you can read it from air standard cycle. The other thing I wanted to say was in the terms of the pH diagram here, You do not actually have a pH diagram for a case like this because it is not a pure substance, but if you treat it as air or if you treat it as a single substance, again air is a mixture, but if you treat it as a single substance you are always talking about the critical point. So you are really looking at this region. All you have is you are starting at some, you are working between two pressures, there is a P1 or P high and a P low, and you are working within two adiabatic processes. So you can start at P low at some temperature and you have an isentropic process that goes up to P high, and then you have heat addition at constant volume. So how will you represent it on this diagram? All you do is go along a constant volume line, and this is isentropic, this is V is equal to constant. Along the constant volume line you have a heat addition, that means temperature. How will I draw this diagram? I have these lines, this is T1, this is T2, T2 less than T1. I have compression from low pressure, this is where I start, let us say this is A. From here I have I go to the higher pressure. I think I should draw this a little lower because getting outside the board otherwise. I go to this pressure, this is B. From there I have a constant volume line which is a different slope, this is the constant entropy line. We have seen that the constant volume lines have a different slope, lower slope. So I have some heat addition, so I will go up to this point C and then come back along an adiabatic, this is D. So A, then B, B to C, this is B, this is C here, and then D. This heat addition is what you have to know, you have to know how much heat is added during that process. So you will have to add the internal energy there and move along that line to the new point. Essentially I will not give it to you in the form of a chart, I mean the form of a graph, it will be given to you in the form of a table. And then there are variations of these that have been discovered through history, but really the Otto and the diesel are the ones that have remained the simplest and the easiest to operate. What I will do is I will, for the sake of completeness, I will discuss refrigeration very briefly on the, although you have done this, because this is called vapor compression refrigeration, which is what you would have done on the pH diagram. And then I want to discuss later absorption refrigeration, which is what is used on large scale. This is work to heat conversion devices. Here you are talking of two phases. What you do is take, let us say, pure vapor, could be freon, now you have non fluorohydrocarbons for this thing, but you have pure vapor which you compress along an adiabatic. I work between two pressures, again I have A, B, this is adiabatic compression from A to B, from B I cool it to saturated liquid, then I carry through an isenthalpic process this is called throttling. So, you bring it down to a point D where you get a mixture of liquid and vapor, and then whatever liquid there is you evaporate here. This is actually I will call this condensation and I will call this evaporation. Evaporation requires that you take heat from the surroundings, QE. Here you add heat when you give up heat. When you condense a fluid, the latent heat is given up to the surroundings. It just happens that you give up heat at a higher temperature and you absorb heat at a lower temperature. Since you are interested in the extent of cooling, the coefficient of performance for such a cycle is the amount of cooling that you produce, which is QE, which is HA minus, write this down, QE by W. This is where the work is. This process, for this isobaric process, the total heat that is removed is HA minus HD. And the amount of work done for an adiabatic system for flow systems per unit mass flowing through the system, it is a difference in enthalpy. So, by HB minus HA, it is called the coefficient of performance. So, if I give you the chart for the fluid, it is absolutely trivial for you to calculate this. You must have done this calculation. This is vapor compression. What we will look at is mixtures where you do absorption refrigeration. You will find that for large scale absorption refrigeration is much better. Here you have a compressor with moving parts, there you do not have the same, what you do is absorb the gas in a liquid and you take away the gas in a liquid at a different temperature. You find that this, you can use this difference in solubilities and the enthalpy of dissolution to do the to extract some refrigeration out of it.